Hi, my name is Dane Christie. I'm a graduate student in the Department of Chemical and Biological Engineering at Princeton University, and today I'd like to share some of the work that I've been doing with you at Princeton. So the focus of my thesis is to characterize the distribution of glass transition temperatures across the domain period of lamella-forming diblock copolymers, and I plan to do so using fluorescence spectroscopy. So we're generally interested in measures of TG because it's the most important property of a polymer, and the focus of the polymer physics community for the last 25 years has been characterizing the size dependence of TG for polymers that are confined to nanoscale dimensions because they have been shown to deviate from bulk. These deviations are related to the nature of interfacial interactions that the confined polymer experiences. So fluorescence spectroscopy was designed as a tool to characterize interfacial effects on the glass transition temperature of these polymers, and its promise is in the local nature of the technique and the ability to spatially resolve changes in properties over very small length scales. So Torkelson and co-workers showed in a singly supported film geometry that the largest deviations in TG are in the vicinity of the interface, and that these effects propagate over tens of nanometers into a film. So in a similar manner, we would like to take this technique that's been developed for a thin film geometry and expand it to a more complex system that may be nanostructured in the bulk. And so I'd start with a diblock copolymer because it's the simplest nanostructured system that you can characterize, and it's a model system. So these diblock copolymers are synthesized by ionic polymerization, and it is a stepwise and living technique that provides precise control over the labeled architectures of the diblock copolymers that you can make. So you can put a probe wherever you would like to along the chain during synthesis. So for a series of labeled diblock copolymers that are represented here in this legend, we can characterize the length scales that are associated with this diblock by using X-ray scattering. Now I'm looking at the location-specific measure of TG, and it's cast in terms of the conversion of PMMA, where we add the probe during synthesis. So what we see from this graph is that relative to the average, the measure of TG at the block junction, or zero, the location that corresponds to zero, is suppressed by about 40 degrees, and that you recover this average value as you move towards the interior of the film. So this variation in TG is due to the difference in bulk measures of the glass transition temperature between the two blocks, and that's about 100 degrees between the PBMA and the PMMA. So hopefully I've been able to show that you can selectively label these diblock copolymers during synthesis and then perform local measures of TG in self-assembled lamella. So the story that comes away from this study is that there's a gradient in polymer dynamics as you move away from the interface, and this gradient is related to the difference in average TGs for the two blocks. So with that, I'd like to acknowledge support from my groups, and thank you for your attention. And if you would like to contact me with more questions about this work, my email is listed below. Thank you.